When you have combined events, 2 events or more, the types of events that can occur are called complementary, mutually exclusive, and independent. And they all have their own definitions that you need to try to understand. First up, if 2 events are complementary, they have to occur separately, but one complements the other. So in other words, the 2 events, such as in this case A inside the circle, and the event that is every thing or every object that occurs outside of the circle, add up to 1, and they complement each other. So they're separate from each other, so that's why I've called this one event A, and the one that's outside in the blue is anything that's not A. And providing this is our total set population or group, and that adds up to 100% of everybody, then we can say that A and A dash are 2 complementary events. So what about our example of drinking coffee or drinking tea? Well, the 2 events, drinking coffee and drinking tea, are not complementary, but if we look at people who drink beverages, and so we regroup the beverage drinkers as those who drink either coffee or tea or both, then they are complementary with the group that doesn't drink beverages, because altogether the 6 events in the beverage group, the 6 people in the beverage group, the 0.6 probability and the 0.4 in the non-beverage group add up to 10, 100%. So we could say that the probability of drinking a beverage, this is a new event now, is complementary with the probability of not drinking a beverage in this case. So we have to define it and be really careful. So there's an example for you. The next definition is mutually exclusive events. Mutually exclusive events are events that exclude each other. So if A occurs, B cannot occur as an event. Here's an example for you. In the 1980s, there was a fella called Al Bundy, and he was like your early modern family, the old Bundys. And if you were Al Bundy, you would probably believe that the event love and the event marriage are mutually exclusive. In our familiar but very handy example of the tea and coffee drinkers in our class, the 2 events of drinking tea and coffee with our sample class, we can see that drinking tea and drinking coffee are not mutually exclusive, and that's because of Sandy. So Sandy is an occurrence or an example of the fact that the events do coincide and they do happen together. Now, just because you're a coffee drinker does not make you not a tea drinker as well, in this case. So they're not mutually exclusive events. There's no reason to suggest that they are. And really the proof is in the fact of looking at this middle overlap, the AND group. The proof is in the fact that the probability of drinking coffee and tea does not equal 0, because it actually equals 0.1. If it equaled 0, then Sandy would not have left her hand up for both, and this wouldn't happen, so you would not get the the Venn diagram overlapping at all, but you would get this. You would get a separation, and you would also see a 0 in the coinciding occurrence of those two events, plus this all-important formula that the actual intersection between coffee and tea would equal 0. Nothing else, not 0.1, not 0.00001, but absolute 0, nothing separation. The third event pattern or type of event is independence. Two events are independent if they do not impact on each other. So they both occur separately and they both have a different rate or probability of occurring, but if one occurs, it doesn't affect the rate that the other occurs, and it doesn't impact on it in any way, and vice versa, so they actually act independently. I was going to suggest that waking up in a bad mood is one event, and I was going to suggest that the weather, being a completely separate event, wouldn't have anything to do with it. But in actual fact, it can, because some people are affected by, say, bad weather. They wake up in the morning, if it's raining, they feel bad. So the rate that we would observe grumpy people in the morning might be higher when it's a rainy day. So they're not independent, strictly speaking. But the only way that we can check for independence is to look at the numbers and to look at this rule and see if it's operating. The rule says that the probability when A and B do occur together, so the overlap with A and B occurring, is separate when we multiply the total probability of A by the total probability of B. So we ask ourselves, is drinking coffee independent from drinking tea? What do you think? When you look at this diagram here, are there any clues in this diagram as to what's going on? So let's say that coffee is drunk. The probability of drinking tea in that case is 0.25. However, if coffee is not drunken by those people, the probability of drinking tea is actually different. So this diagram here suggests that they're not independent. Otherwise, whether we have drunk coffee or not would not affect the rate of drinking tea. We'd have an even split through this pair of branches and through this pair of branches as each other. They'd be the same. But we can see that it's not. Now, in terms of this rule here, we look at the actual absolute crossover of drinking of the two events occurring, coffee and tea. And from our diagram here, it's 0.1. And from our table here, where the absolute data lies, it's also, we can see it's 0. So probability, coffee and tea combined, working together in actual life. And I have to say that thanks to Sandy, who does do both, and she's our proof, our evidence is 0.1, or 1 out of the 10 people in our sample. But the probability of drinking coffee of the probability of drinking tea is in fact the coffee rate, which is 0.4. We get that from our table here, multiplied by the tea rate, which is 0.3. And we find that here, 3 out of 10 people. So this is drinking tea, just the whole PT business, 0.3. Just the tea club multiplied by the independent, just the coffee club. And if they were independent, we would actually expect that 4/10 of 3/10 would be the cut or the rate that would evenly occur with the two events occurring together. But 0.4 times 0.3 is 0.12, and that is actually not equal to a tenth. It's a little bit higher than we would expect. So that is our proof, mathematically and numerically, of what we observe here, where the pair of branches here is different from here, where the rate here, 1 and 4, is different from 2 and 6 here, and I'll just describe that again. If coffee is drunk in this column here, the tea rate of drinking tea is 1 and 4, which is 0.25. However, in this column here, if coffee is not drunk, the rate of drinking tea, or the proportion of people who drink tea, is 2 in 6, which is 0.33. So we have a split out of the tea rate occurring.